From a distance, Mount Adams looks almost too peaceful to belong among the great volcanoes of the Cascade Range. Its enormous snow-covered summit rises to 12,277 feet, or 3,742 meters above sea level, making it one of the highest peaks in Washington. Forests climb its lower slopes, glaciers occupy the upper mountain, and broad valleys spread outward in every direction. Yet despite its immense size, Mount Adams receives far less attention than Mount Rainier or Mount St. Helens. Rainier dominates the skyline near the heavily populated Puget Sound region, while St. Helens became internationally famous after its catastrophic eruption in 1980. Mount Adams has remained comparatively quiet, but that quiet mountain hides an extraordinary volcanic history. Mount Adams is not simply one of Washington's largest mountains. It is the largest active volcano in the state, when measured by area and eruptive volume. Over approximately the past 1 million years, the volcano has produced roughly 300 cubic kilometers, or about 72 cubic miles, of volcanic material. That is an enormous quantity of lava, ash, volcanic rock, and other deposits accumulated through countless eruptions. Only Mount Shasta in California has produced a greater volume among the Cascade volcanoes, with approximately 350 cubic kilometers, or about 84 cubic miles. The scale becomes even more remarkable when the entire Mount Adams volcanic field is considered. This enormous landscape covers approximately 500 square miles, or about 1,300 square kilometers, and contains more than 112 volcanic features. Those smaller features reveal something important about the mountain. Mount Adams is not simply a single cone rising from an otherwise ordinary landscape. It is the central expression of a much larger volcanic system. Scattered across the surrounding field are cinder cones, shield volcanoes, lava flows, spatter cones, and other volcanic structures formed during different periods of activity. Volcanism in the region began approximately 940,000 years ago. The main Mount Adams edifice began developing roughly 520,000 years ago, more than 500,000 years in the past. Early volcanic activity occurred several miles or several kilometers southeast of the present summit before the main center gradually shifted toward the location of modern Mount Adams. Over hundreds of thousands of years, repeated eruptions slowly constructed the enormous mountain that dominates the landscape today. The volcano did not rise in a single dramatic eruption. Instead, Mount Adams was assembled gradually through repeated episodes of volcanic construction. Lava flowed from different vents, volcanic debris accumulated around eruptive centers, and successive eruptions added new layers to the growing mountain. Scientists identify several major periods of construction, including episodes roughly 500,000 years ago, 400,000 years ago, and another major period between approximately 50,000 and 30,000 years ago. During these later stages, lava flows helped build much of the mountain recognizable today. Some ancient flows traveled approximately 9 miles, or 15 kilometers, from their sources. Over immense spans of time, these repeated eruptions created a huge volcanic edifice whose slopes were later carved by glaciers, rivers, landslides, and erosion. That combination of construction and destruction continues to shape Mount Adams. Volcanism builds the mountain upward, while gravity, water, ice, and weather gradually tear it apart. During periods of intense glaciation, enormous quantities of ice covered the upper slopes and carved deep valleys into the volcanic rock. Glaciers removed material from the mountain and helped create many of the valleys that later became pathways for rivers and volcanic debris. At the same time, hot fluids circulating inside the volcano altered portions of the rock. Hydrothermal alteration can transform strong volcanic rock into weaker material by changing the minerals that bind the rock together. On Mount Adams, this process has created large areas of weakened material, especially beneath portions of the upper southwestern flank. That weakened rock is one of the most important reasons scientists pay close attention to Mount Adams. A volcano does not have to erupt explosively to become dangerous. Sometimes the mountain itself can collapse. When volcanic rock becomes heavily altered by hot fluids, it can lose much of its original strength. Cracks, fractures, water, ice, and gravity can then combine to destabilize steep slopes. On Mount Adams, scientists have identified an enormous volume of hydrothermally altered rock beneath the upper southwestern part of the volcano. Estimates suggest that this weakened mass could contain as much as 1.3 billion cubic meters, or approximately 46 billion cubic feet, of material. That does not mean such a collapse is imminent, but it demonstrates why the volcano's hazards extend beyond conventional eruption scenarios. Mount Adams has already demonstrated that large slope failures can happen. Approximately 6,000 years ago, a massive portion of the southwestern flank collapsed. The debris avalanche contained approximately 0.07 cubic kilometers, or about 0.02 cubic miles, of volcanic material. The collapse devastated approximately 14 square kilometers, or roughly 5.4 square miles, of the mountain's southwestern flank. But the event did not end at the base of the volcano. Once the enormous amount of loose volcanic debris entered the surrounding drainage system, water transformed much of it into a powerful lahar. The mixture of mud, rocks, water, and volcanic debris traveled downstream through the White Salmon River system and eventually spread across the Trout Lake lowland. The scale of that ancient lahar is difficult to appreciate from the peaceful landscape visible today. Deposits from the event cover approximately 15 square kilometers, or nearly 6 square miles, across the Trout Lake region. In some places, the volcanic debris reached approximately 65 feet or 20 meters thick. Geological evidence indicates that material associated with the event traveled as far as Husum, approximately 37 miles or 60 kilometers from Mount Adams. The event happened thousands of years before modern communities, highways, bridges, farms, and utilities existed in the region. Yet the pathways carved by rivers have changed far less dramatically than human civilization. The same valleys that carried prehistoric volcanic debris remain natural channels through which future lahars could potentially travel. Mount Adams experienced another significant slope failure approximately 300 years ago. A large mass of altered material collapsed from the southwestern side of the volcano and generated a lahar that moved into the Trout Lake lowland. In geological terms, 300 years is an extremely short period. The event occurred after human societies were already established throughout the Pacific Northwest, demonstrating that large debris movements are not restricted to some impossibly distant prehistoric era. The volcano has continued to shed material during more recent times as well. These events provide scientists with an important record of how the mountain's weakened slopes behave. They also demonstrate why hazard assessments cannot focus exclusively on the question of when Mount Adams might produce its next eruption. One of the clearest modern examples occurred in 1921, when approximately 4 million cubic meters, or about 5 million cubic yards, of altered rock collapsed from the head of Avalanche Glacier on the southwestern side of Mount Adams. The debris traveled almost 4 miles, or approximately 6 kilometers down Salt Creek Valley. Parts of the material transformed into smaller lahars as water became incorporated into the moving debris. The event was far smaller than the enormous prehistoric collapse, but it demonstrated that the mountain's altered slopes remain capable of failure even without a major volcanic eruption. Similar smaller debris avalanches have occurred in more recent decades. Mount Adams therefore possesses a hazard that can operate independently from an eruptive crisis. This is a crucial difference between volcanic hazards and the popular image of an erupting volcano. People often imagine danger beginning when a mountain suddenly produces lava, ash, or an enormous plume. But at Mount Adams, a major hazard could potentially begin with a landslide. If enough volcanic material collapses from the mountain and enters a river system, the resulting debris flow could travel far beyond the original failure. Water is the key ingredient. A landslide becomes much more mobile when it mixes with water, and volcanic mountains contain enormous quantities of snow, ice, groundwater, and surface water. That combination creates the potential for lahars, which can behave like rapidly moving concrete and carry boulders, trees, mud, and other debris downstream. The southwestern side of Mount Adams is particularly important because of the enormous volume of weakened volcanic material concentrated there. Scientists estimate that the altered mass could contain as much as 1.3 billion cubic meters, or roughly 46 billion cubic feet of rock. That figure does not represent the amount that will necessarily collapse in a single event. It is an estimate of the potentially unstable material within the altered region. A large failure would require specific conditions and would not automatically occur simply because the material exists. Nevertheless, the geological record shows that this part of the volcano has failed before. That combination of past collapses and present-day geological weakness is why the southwestern flank remains one of the most closely considered hazard zones around Mount Adams. Another area of concern lies on the eastern side of the volcano. There, scientists have identified a smaller region of altered and weakened rock containing approximately 12.5 million cubic meters, or around 440 million cubic feet of material. Compared with the enormous southwestern mass, this eastern volume is much smaller, but it demonstrates that hydrothermal alteration is not confined to one isolated portion of Mount Adams. Volcanic systems are complex environments where heat, fluids, fractures, and changing pressures interact beneath the surface. Over thousands of years, those processes can weaken portions of the mountain. Gravity then constantly pulls on the altered rock. Most of the time, nothing catastrophic happens, but the geological record proves that large failures are possible, which is why the mountain slopes deserve attention even during periods of apparent calm. The greatest hazard at Mount Adams is therefore not necessarily a giant explosive eruption. Lahars and debris avalanches are among the most important threats. A future lahar could begin with a volcanic eruption that melts snow and ice, but it could also result from a large landslide that occurs without an eruption. Once volcanic debris enters a river channel, the surrounding landscape can determine where the material travels. Valleys become natural conduits, rivers provide water, steep slopes provide sediment. The combination can transform a local collapse into a regional event. This is why communities downstream from Mount Adams are included in volcanic hazard assessments, even though they may be many miles or many kilometers from the summit itself. Yet Mount Adams is not primarily known for producing the enormous explosive eruptions associated with Mount St. Helens. Its eruptive history has generally been dominated by lava flows and relatively modest explosive activity. The volcano has produced lava from vents near the summit and upper flanks, and many of its flows traveled relatively short distances. Recent lava flows have extended approximately 4 to 7 miles, or about 7 to 12 kilometers, from the summit to the base of the volcano. Most lava flows have traveled less than 12 miles, or 20 kilometers, from their vents. These flows could still destroy forests, roads, structures, and infrastructure in their path, but their relatively slow movement would generally provide more time for people to respond than a fast-moving lahar. Rarely, however, Mount Adams has produced much longer lava flows. Some of the more voluminous flows in the volcano's long history traveled approximately 15 to 30 miles, or about 25 to nearly 50 kilometers from their sources. These ancient flows demonstrate that the volcano's lava-producing system can operate on a much larger scale than the more recent flows near the summit. Even so, the geological record indicates that Mount Adams has generally behaved as a relatively effusive volcano compared with the highly explosive Mount St. Helens. That distinction is important because volcanic danger is not determined simply by the size of a mountain. A huge volcano can have comparatively gentle eruptions, while a smaller volcano can produce devastating explosive activity. The most recent recognized eruption of Mount Adams occurred several thousand years ago. The exact timing varies somewhat depending on which deposits are considered, but geological evidence places the latest eruptive activity within the Holocene, the geological epoch that includes the development of human civilization. That fact matters because Mount Adams is not an extinct volcano whose activity ended millions of years ago. Its volcanic system has remained active on a geological timescale, and there is no scientific basis for assuming that the last eruption was its final one. The mountain may remain quiet for centuries or longer, but eventually another eruption is expected. The uncertainty is not whether Mount Adams can erupt again. The uncertainty is when, where, and how large that future eruption will be. The future eruption will probably not resemble the 1980 eruption of Mount St. Helens. Mount Adams has a different eruptive history and a different volcanic architecture. The most likely future activity would involve relatively small eruptions of lava and tephra from vents near the summit or upper flanks. Tephra includes fragments of volcanic material ranging from tiny ash particles to larger pieces of rock thrown into the atmosphere during an eruption. Such an eruption could still create serious local hazards. Lava could bury roads or forests. Falling ash could reduce visibility and affect machinery. Volcanic gases could create dangerous conditions close to the vent. And if an eruption interacted with snow and ice, lahars could become a major concern. Mount Adams represents one of the most fascinating contradictions in the Pacific Northwest. It is enormous, yet often overlooked. It is active, yet usually quiet. It has produced eruptions, yet its most important hazard may come from landslides and lahars rather than explosive volcanic columns. It contains immense quantities of weakened rock, yet there is no evidence that a catastrophic failure is imminent. Its slopes preserve evidence of events thousands of years old, while smaller failures have occurred during modern times. The mountain's danger is therefore not a prediction of disaster. It is a recognition of geological reality. Mount Adams has repeatedly demonstrated what it can do, and those ancient deposits remain part of the landscape surrounding communities today.